Hello everybody and welcome to the NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 15 and we will continue from where we left in the previous lecture. We will look into the subthreshold region of operation of a device and then deep dive into the cryogenics part of electronics. What are the various terminologies used? How do you define cryogenics? What is the meaning of cryogenic and so on and so forth. So, with that background, let me start today's lecture. Let's look at the subthreshold conduction part first of all, right? And then we can go step by step as we move ahead out of it. Now, if you remember, there were two modes of operation of a device. One was post threshold, another is subthreshold. How did you define threshold by my previous definition? The threshold was defined as that voltage at which the channel is formed just below silicon dioxide interface, and you have as many number of electrons in case of an n-type semiconductor as the number of holes were there initially in that place. So, if you had say 100 holes per unit volume or per unit area of that in that space, now you have 100 electrons. That is what we defined as the threshold voltage, right? We defined that as the threshold voltage here, and in many books or many places you will written as VTH or VTH. This is the notation which people follow, right? Now, the idea here is that though for a substantial amount of output current, you should have a channel being formed, then only there will be large amount of electrons flowing from source to drain. But I can easily actually reduce the number of carriers by applying my gate voltage just near or just below the threshold voltage. I will still have the current being flowing, but it will not as large as it would have been in saturation. And that is the reason we define that to be as the weak inversion layer. Weak inversion layer is when the gate voltage is approximately equals to VTH or even slightly less than VTH, not very low. If it is very low as compared to VTH, then the device will go into the off state. So, there are three states which you remember, that gate voltage is greater than the threshold voltage, right? Then we and if my drain to source voltage is greater than VGS minus VTH, we define this to be as the saturation, and there will be a current equation associated with it. And the current equation will have a direct dependence on the aspect ratio W by L. Higher the value, higher will be the current flowing through the device in saturation. But what we have done here is that we have knowingly kept my gate voltage just below or equal to the threshold voltage. Then what happens is that the number of carriers, inversion carriers, will not be the same. Nonetheless, it will be slightly less than that, and still there will be some current flow. And that region of operation is therefore referred to as the weak region of operation, and we define that as the weak inversion layer is formed. And we define when VGS, and this condition is referred to as sub threshold, which is less than threshold. So, when that is the reason, if you look at the third bullet here, when VGS is less than VTH, the current will be finite, but it exhibits an exponential dependence on the value of VGS, and that is referred to as the subthreshold conduction, right. You see, you just look at the statement here that some chi and VT is basically KT by Q if you look very carefully, and this is approximately equals to 25 millivolts at 300 Kelvin. So, at 300 Kelvin this is approximately 25 millivolts. So, at 300 Kelvin you do not have to worry, you can just plug the value of 25 millivolts at this particular point. Eta is typically taken to be 2. So, 2 into 25 is, you will get approximately 50 millivolts at the denominator of this expression. I naught is basically the zero current or the current at very low currents when your exponential e to the power some quantity goes to 1 e to the power 1 when approximately, that is the value of I0, and VGS is in the numerator. Now, what the idea here is that as you go on increasing the value of VGS in the subthreshold domain, your ID has an exponentially dependence on VGS, which means that if you look at the current characteristics, ID is proportional to exponential VGS, which means that for a small increase in the value of gate to source voltage, you would possibly get a very large change in the value of the drain current, right. And therefore, in the weak inversion, the current is very sensitive to the variation of the gate voltage. So, the takeaway from this discussion is that you can operate your device almost near the threshold voltage of the device or just near the threshold voltage of the device and still have, if not very large, substantial amount of current which will be actually defined as the leakage current. Why leakage? Because your device is not considered to be on, because gate voltage is not greater than threshold voltage, right. Though it is not on, but still you have some current flow available to you, and that is how you define as the subthreshold conduction. So, subthreshold conduction, also referred to as a leakage, is what you see in front of you. Many a times I do not want the devices to operate always in the saturation region, I want to operate in the subthreshold conduction, then my currents are small and I ensure that my power dissipated is also small. So, if you want to design a low power design technique, one of the methodologies is basically your subthreshold conduction. This is what we learned from this one. Let us come to the same expression and let us plot it here. Now, let us go one by one. I am plotting log of the drain current here on the y axis to that of the gate voltage here on the x axis, right. The point of inflection is basically the threshold voltage, right. The threshold voltage is the point of inflection. If you remember, we just now were discussing the previous slide. I had this ID equals to I naught exponential VGS by KT. So, let me just write it down. ID will be equals to I naught exponential VGS by eta times VT. This can be written as I naught exponential VGS, assuming eta to be equals to 2, VT to be equals to 25 millivolts. This is approximately 50 into 10 to the power minus 3. This is the value of drain current at subthreshold region, right. Which is the subthreshold region? This region is defined as my subthreshold here, where you have an exponentially dependence of current with respect to gate voltage, and therefore you see this is basically small, an exponential is becoming a linear in the log scale, and that is the reason while you look at it, it looks like a linear variation. There is a terminology which is referred to as subthreshold slope, which means that for a 1 decade change, right, change in drain current, how much change in gate voltage is required. So, which means that if I want that the current should go from 10 to the power minus 5 to 10 to the power minus 4. So, this is a 1 decade increase in the current. Then to go from this point to this point, how much change I should go for the gate to source voltage is referred to as the subthreshold slope, and the subthreshold slope is given by the units of this is millivolts per decade. It is millivolt per decade, which means that for every 1 decade change in current, how much millivolt change in the gate voltage you want. Say this is written as 80 millivolts here. It primarily means that for 80 millivolts change in the gate voltage, I would expect to see a 1 decade change in the current. Since this is a log scale, so I can safely say, suppose this is 10, then this will be basically here will be 10 to the power 1, 10 to the power 2. This will be 10 to the power 2, right. And this change, so this comes out to be 10, and if I proceed it forward, it comes 10 to the power 2. Then this is basically your change in the delta VGS, and this change is basically delta ID, delta log of ID actually, 1 decade change. So, we define subthreshold slope as del VGS, right, upon del log of ID, right. Or another way of writing it is that we write del of log ID divided by del VGS, 1 divided by this whole quantity, it becomes del VGS by del of log ID. And as a designer, be it cryogenics or room temperature electronics, you need to ensure that this value should be as low as possible, which means that for a small change in the value of VGS, I should get a very large change in the current, and that shows to me the sensitivity of the device will be much larger. What is the sensitivity to? Sensitivity to the input signal variations. So, you are giving the input signal on the gate side, and because of the gate side showing a change, you get a decade change in the current. Now, so we have concentrated and understood about this part. Let us concentrate on this part. This is the part where, assuming that my drain voltage is relatively large and I am able to sustain this inequality VGS minus VTH, I will not be able to do it for low values of the gate voltage, but as my gate voltage increases, I will be able to do it. And if you remember your basic MOS device, then ID in this case was given as mu L C oxide into VGS minus VTH whole square. You see, there is a square law dependency. So, you have a square law dependency in the saturation region, and you have an exponentially dependency on gate voltage in the subthreshold region. Somewhere in the middle, which is this one, is the point where you have the connectivity between the square law and the exponential law, right. And you need to actually ensure that at this point there is a continuity in the current equation. So, we have learned one important point here, that if you do a subthreshold characterization or characteristics, you need to ensure that square law is valid beyond threshold voltage, and also you need to ensure that the exponentially dependence of drain current on the gate voltage is valid below the threshold voltage, right. However, and this is where you will learn one of the first trick or nuance of cryogenic, that as you lower the temperature of your device, the threshold voltage itself starts to change, right. And why and how we will see later on, but primarily it changes drastically. So, let us assume that the threshold voltage shifts to the left, right. Then if it shifts to the left and this is the new point, then what I will see is this will be like this, and then you will have a fresh value of current, right, or maybe something like this, and then it will come something like this, right. So, we will study this in detail, but please understand, at room temperature threshold voltage is constant, assuming nothing is changing. Then however, in cryogenics threshold voltage will be a function of temperature, and we need to be very careful in defining the exponential region and the square law region of the MOS subthreshold characteristics. So, what is the advantage of having MOSFET in subthreshold region? Obviously, as you can understand, the currents are relatively small, right. The currents are small will mean that the power which you dissipate will be smaller, right. So, the heating effect will be reduced drastically when you have the MOSFET operating in the subthreshold region of operation. As you can see, since current has an exponentially dependence on the voltage, we define a term known as transconductance, which is del S del VGS, right. Since it is an exponential dependence, this variation is pretty large, right, and therefore, this is very large, which means that if I do this GM times the output resistance, then this is also very large, because GM is very large, right. So, transconductance does not give you an idea about the absolute value of the drain current, but gives you an idea about the rate of drain current change with respect to gate voltage. And higher the value it is, more sensitive to use your device to variations in the input voltage, and that is the reason we write down gain is achieved. But please do not take this very seriously, the last statement here. There is a reason why, because the absolute value of current is so small that even if the change is very large, I will not be able to sustain a very large voltage drop at the output side. So, keep this into your mind while designing or understanding this whole issue. Apart from this, since it is exponentially dependent, you will have other advantages operating in the subthreshold region of operation. What are the disadvantages? The disadvantage is something like this. Since your currents are very small and it is an exponentially dependent on VGS, but the current absolute value of currents are very small, the speed of the circuitry actually reduces, and therefore, what you see is you will have latency which is high. So, if you operate your devices in subthreshold region of operation, since your currents are small, your latency is large, and you will ask me why is it like this? It is very simple and easy to understand. If your current is small, then you will require a larger amount of time to charge or discharge the capacitor. So, let us suppose I have a circuitry, some circuitry black box, and there is a capacitor connected, always there will be a capacitor connected here, and you are operating this circuitry in subthreshold region of operation. While you are operating it, you do what? The current which is flowing through this network ID is very small, and therefore, the time taken to charge or discharge this capacitor, and therefore, this voltage to go to 1 or to 0 in case of digital logic design, this takes more and more time, whereas the current would have been larger, with the lesser time I would have been able to charge or discharge the capacitor. So, that is the reason, that is the second point which I have done. Then the previous advantages which I showed it to you 1, 2 and 3, they can be met for large widths or low drain currents, either of the two cases. A large width or low drain currents advantages you will be meeting with that, but if you have a large device width, then effectively your area of the device becomes larger and you end up having a larger area. Whereas, if you have a low drain current, you know there will be always a problem of the speed being severely limited. Now, the next aspect is, and that is very critical for this specifically this course, that the effect of temperature on drain current is high, right. I will explain to you how. You remember that as the statement which I was writing here in your case, I equals to I naught exponential VGS by eta times Vt. This is Kt by Q. and this is temperature dependent. So, as you reduce your temperature, right, as you start reducing your temperature, this quantity starts to fall down, which means that this quantity starts to fall down. Denominator falls down means my current becomes larger and larger, which means that there is surely a effect of drain current in the subthreshold region because of temperature, right. That is one thing which you should be very careful, because that is one of the sort of talking points for low temperature design, that since temperature will drop down, there will be change in the driving capability of the device. Moreover, please understand one important point. Since the current is very, very low, the change will be relatively large. Something like this, that if you have let us say 100 electrons here and 10 electrons here, and you are adding 10 electrons here and 10 electrons here, here I see almost 100% change in the electron population, whereas here I will write down as 10% change in the population. So, smaller the value, higher the sensitivity is in terms of percentage in the output side, right. That is what I just wanted to give you an idea about the operation here. With this, we have taken care of the basic idea of subthreshold. Let me now come to the measurement setup which you see in typical cryogenics and electronics application and emerging trends in cryogenic electronics. Now, we all know, and I will again reiterate, that cryogenics is the study of materials and systems at extremely low temperature. When I say extremely low temperature, it typically mean around 4 Kelvin and below. So, typically around 10 Kelvin and below, you will have absolutely very, very low temperature. Absolute, we will never reach to absolute 0. It is technically not feasible to reach to 0 Kelvin, but 10 Kelvin, anything below 10 Kelvin is extremely low temperature, and we say that we have reached to the cryogenics. As I discussed with you, cryogenic originates from Greek word cryo, which means cold, and then what we will study is how does the material behave at such low temperature conditions, right? Where will it behave? Now, you will ask me why is it used? Many applications, we will go one by one, but most important sort of application of cryogenics as of now is in two areas. One is when you work with deep space exploration and your electronics has to work at extremely low temperature, minus 150, minus 160, minus 170, at that such a low temperature, you need to design and model it at for low temperature. And the second, which is coming up in a big way, is basically my quantum computers. So, in these two places you will see much use of these materials. So, there are materials or substances known as cryogens, such as liquid nitrogen and liquid helium. So, this is liquid nitrogen and liquid helium. These two are the known and proven sort of cryogens which are available to us in this case. Okay. And the liquid nitrogen is of course used most commonly in cryogenics, and the typical temperature it goes down up to approximately 70 to 80 Kelvin, 70 Kelvin to 80 Kelvin. If you go to, this is for liquid nitrogen, and if you go for liquid helium, the same chuck can be brought down to temperature of the order of 4 to 10 Kelvin, right. These are closed loop systems which are able to sustain such low temperatures, and cryogenics have typically boiling points of minus 150 degrees centigrade. So, this is how cryo CMOS dilution refrigerator looks like, where you have for quantum computing purposes. So, that is the reason I am showing you this measurement. So, you know at the end of the day where these devices or systems or subsystems can be used. And this is the measurement setup for cryo CMOS with chipsets. So, this A part, if you look, this A part is basically referred to as a dilution refrigerator, right. It is a long sort of cylindrical column, as you can see on the left hand side of the figure, and there are large number of wires running through it in a parallel session, and the ASIC or the chip which you want to measure is actually placed somewhere at point number C, very close to low temperature region, right. And this is the qubit where you are storing the information, and this is my readout circuitry across which I am trying to read out the value of 1 or 0 in a qubit, right. So, the C is the qubit package which you see, right, and this is the micrograph of the qubit which is generally kept at very, very low temperature. So, this is where you want to keep the qubit temperature to approximately 4 millikelvin. Not only that, let's look at the logic of why we are using these qubits in a sense to a larger extent. The reason is that if you keep your readout, but when I say readout, I mean to read the state of the qubit. I need to either from an external source send an wave which is RF in nature. It strikes the qubit. When it comes back, there will be change in the S parameters, and from S parameter I will be able to predict the state of the qubit. However, if the temperature of the electronics is higher than that of the qubits itself, you might have a large amount of noise available to you which is inserted with the signal itself. So, your signal to noise ratios will actually drop down, which you do not require, especially in the case of a CMOS cryo qubit in that case, right. And that is the reason the electronics is actually inbuilt very close to the cryo station. So, I have a dilution refrigerator, right, and this is a very liquid having quantum processors. I do have an ASIC enclosure, which is a special circuit for quantum computing, right. Obviously, I will have a qubit package where I will place the qubits for manipulation, third one. And finally, what I am showing in the previous graph, point D is the micrograph of the chipset. Again, this is the general picture on the left hand side and then specific picture on the right hand side. The general picture on the left hand side shows you the Devar. Devar is a place where you can actually put in liquid nitrogen or liquid helium in a closed circuit condition. So, this will be ultra vacuum will be created. As you move from top to the bottom, the temperature goes on rising, right, and the lowest one is the temperature where you keep the qubits at very low temperature. And this is the right hand side is basically the needle where you put the probe inside and you try to extract the value of current and voltage through this region. So, I have a dilution refrigerator and it is used to cool an ASIC enclosure which is kept at 3.5 Kelvin and the qubit package at 10 millikelvin. The thermal conductivity is given and the total heat dissipation at 3.5 Kelvin is given as 550 microwatt. So, you need to find the heat flow from 3.5 K to 10 millikelvin. Now, the heat flow is given by the Fourier law, which is Q equals to K into delta T, right. That is the standard way of looking at it. Q equals to K into delta T. K is already known to you, delta T is 3.5 Kelvin to this is 0.1 Kelvin and this is 3.49 Kelvin which you get. So, Q will be 0.1 multiplied by 3.49 which is 0.349 which is 349 milliwatt. For every extraction of data, you require to have a 350 milliwatt of power being dissipated, right. Obviously, when you do a 10 millikelvin stage, the power dissipated is 3.49, right. So, what are the benefits of cryogenics in electronics? The first benefit is of course, you can bring in large amount of carrier mobility enhancement. You can work with good amount of band gap engineering to have various types of interfaces available to you. And then at low temperature, you are actually reducing the scattering and thermal generation. So, those happen to be very large at T equals to 300 Kelvin, but when you talk about T equals to 10 Kelvin or below, you will have a reduced thermal generation and scattering, and there will be obviously the quantum effects of it affecting the device. Let us look at the application of the cryogenics electronics, primarily qubit development and qubit, the place where you will be putting the qubit. You do not see, why do you want to keep it also at low temperature? You do not want its spin to get influenced by an external heating source and so on and so forth. So, what you do is that you try to have the semiconductors also built very near to the qubit value itself, right. They are also vital for electronic systems on satellites and spacecrafts typically, and there is a large amount of study also that if you reduce the temperature to very low value, what will be the effect on the overall device and the circuit characteristics. There is also good amount of ultra low noise measurement techniques available, which will be very useful for cryogenic electronics. Let us look at the emerging trends in cryogenic electronics. The first is incorporation of nanoelectronic devices into cryogenics. We are looking at cryogenic CMOS, which means the temperature is around 10 Kelvin and below, and there are other applications such as deep space exploration I discussed with you, sustainable aircraft development and medical diagnostics, right. They all happen in very low temperature or ultra low temperature. Now, when you maintain that for ultra low temperature, you also pay the price of other parameters also getting inserted with those parameters such as deep space, medical diagnostics and sustainable aircraft engine development. So, let me recapitulate what we did for the previous half an hour. We looked into first of all subthreshold logic. and subthreshold conduction. Then we went for analytical expression for subthreshold logic. Then the third part is, of course, we looked into the meaning of subthreshold itself, subthreshold, and finally we ended up understanding the trends and applications of cryogenic electronics. So, we looked into trends and application of cryoelectronics, right. So, with this, let me finish this talk, and when we meet next time we will start with the next chapter. Thank you.